Hello everyone, and welcome to my M4 final hackathon presentation. My name is Yixun, and today I'm very thrilled to walk you through my project on building a Delbat risk classifier. My final goal was to optimize the F1 score under severe class imbalance while validating my model's overall ranking compatibility. So let's dive right in. My primary objective is to predict diabetes risk using the BRFSS survey data. In this public health screening task, the biggest challenge I face is strong class imbalance. Diagnosed patients are always the minority. Because of this, my primary evaluation metric is the F1 score. However, I also heavily prioritize the ROC AUC metric. Why does AUC matter so much here? The F1 score requires a rigid hard threshold, but in real-world healthcare, assigning a continuous risk ranking is far more actionable than a simple binary label. AUC evaluates my model's pure ranking compatibility, ensuring that a high-risk patient is consistently scored higher than a healthy individual. This gives healthcare providers the flexibility to adjust the decision threshold based on their specific policies. Before jumping into modeling, I performed robust feature engineering. I handled missing values using median imputation to reduce information leakage and minimize the impact of outliers. More importantly, I added interaction features such as combining BMI with age or BMI with high blood pressure. My rationale here was to capture nonlinear health risk effects that simple linear models often miss. On this slide, you can see the distributions of key features like high blood pressure, cholesterol, or BMI after my preprocessing steps. By standardizing these continuous features and creating proper categorical encodings, I significantly improved the signal-to-noise ratio. This step ensures that my gradient-based models treat all physiological measurements fairly without being skewed or by different measurement scales. And these interaction terms help models capture patterns that purely linear relationships might miss. Moving on to my modeling strategy, I established my baseline using logistic regression. It is highly interpretable, but it has limited capacity for complex non-linearity. To break through this performance ceiling, I introduced tree-based models, XGBoost, LightGBM, and CatBoost. These models are exceptionally good at capturing the complex physiological interactions I just mentioned. As I evaluated these models, I found that an ensemble stacking approach further improved both my F1 and AUC performance. From a business perspective, the higher performance of these advanced models directly translate to a higher recall. This is crucial because it reduces the number of missed high-risk patients in a clinic setting. Next, I addressed my biggest hurdle, class imbalance. Instead of using native resampling techniques, I applied class weighting, such as scale pose weight, to force my models to pay attention to the minority class. Furthermore, I configured my model to output continuous probabilities rather than just fixed 0 or 1 predictions, allowing me to search for the optimal decision boundaries. And in medical risk screening, using a default 0.5 decision threshold is highly suboptimal. For example, here, my best single model here is HIST-GB, and with a best threshold around 0.23, giving F1 around 0.466 and ROC AUC around 0.826. Then I looked at the ROC curve and the PR curve to understand performance trade-offs. The PR curve is especially important under class imbalance because it focuses on precision versus recall behavior. To assess and improve fit, I used a stratified k-fold cross-validation. Stratification ensures that each fold preserves class proportions, which matters a lot with imbalanced data. I also used out-of-fold predictions to estimate performance more honestly. Compared to a single train test split, this improves performance stability and reduces dependence on one lucky or unlucky split. Here I overlay the top 3 models by best F1 and show their precisions, recall curves, and ROC curves using OOF predictions. This visualization makes it easy to compare models in a threshold-sensitive way, and also to compare their overall separability under AUC. This picture shows the ROC curves using OOF predictions. To fully understand the medical impact of this 0.23 threshold, let's look at the confusion metric data. I assigned a cost penalty of 5 to false negatives and 1 to false positives. My result shows 50,133 false positives, but I successfully compressed false negatives down to 5,933. This resulted in a total cost score of 44,798. And while 50,000 false positives might seem high in public health, this is a necessarily strategic trade-off. A false positive simply means an unnecessary follow-up blood test, which carries a very low medical risk. However, a false negative means missing a patient critical intervention window, leading to a severe complication and a massive healthcare cost. This strategic trade-off is exactly why I heavily relied on the precision recall curve, which is shown here. The PR curve is highly preferred under severe class imbalance because it focuses specifically on the positive minority class. It helped me visually pinpoint exactly where my F1 score peaks before precision drops too drastically. To summarize my fit diagnostics, analyzing the confusion metric and PR curve together proves that my threshold tuning was not just a mathematical trick, but a deeply business-aligned decision. I intentionally trade a drop in precision for a necessary boost in recall, perfectly align the model with real-world public health priorities. And beyond threshold tuning, I needed to diagnose my model's overall fit to ensure I wasn't just memorizing the training data. To do this, I utilized learning curves to check for overfitting and underfitting. I implemented mitigation strategies like L2 regularization, tree depth limit, and stratified k-fold cross-validation to control the model's complexity. As shown in this learning curve plot for light GBM, my strategies worked. You can observe a very healthy, narrow gap between the red training score and the green cross-validation score. Both curves stabilize nicely as the sample size increases. This proves that my model generalizes well to unseen data and does not suffer from severe overfitting. Looking ahead, If this model were deployed as a real-world clinic tool, I would incorporate external data such as macroeconomic indicators, lifestyle logs, and detailed clinical records to build a more comprehensive risk profile. Furthermore, I would actively monitor for data drift using the population stability index. If underlying uh, demographics change over time, I would implement a champion challenger framework to seamlessly retrain the model. And that is all about my project. Thank you for your time, and I'm very happy to take any questions.